Hello and welcome to our presentation today. Today we're going to present about reproducible research and building business continuity into your lab. This is for the LADAL Opening Webinar Series, and my name's Amanda. I'm Griffith University in QSIF as an e-research analyst, and I'd also like to introduce Julie Toohey.
Hello, I'm a library research specialist at Griffith University.
And today we're very excited to present this to you. I'd like to acknowledge the traditional custodians of the land of which we're meeting and pay respect to the elders, past and present, and extend that respect to all Aboriginal and Torres Strait Islander people. So, you've heard about reproducible research, but what actually is it? It's the idea that, say, if somebody's completed a project or released a paper, if you were given the raw data they started off with and the information they've provided, could you follow all the different steps that they've taken and redo all their steps and come up with the same conclusion? So the idea is that there is enough information in there about what they've done and the data that they supplied that it should be all the same. So why is this important? All our knowledge is based on knowledge that's been built previously. So things like scientific papers, research journals, all base their information on previous papers that have been published. And so we need to ensure that whatever papers have been published prior to us are true. Their information is correct and their stuff is reproducible, because it means that if we're basing something on a paper that isn't true or isn't reproducible, we might not be able to rely on that. Nature did a study in 2016 around reproducibility and how 1,500 scientists had found, both trying to replicate their own papers or somebody else's. In medicine, the numbers were pretty high, so over 60% of people who'd attempted to replicate somebody else's paper failed to do so. But not only that, over 50% of people who tried to replicate their own paper weren't able to do so. This is a massive number, and it can point to not necessarily that the papers are wrong, but that there's not enough detail in the paper to be able to replicate the research. But it does mean that these papers aren't able to be verified, and that's a massive concern. In some other fields like chemistry, over 80% of people who had tried to replicate somebody else's paper failed. So as you can imagine, this is a pretty big issue. But however, there's a lot of steps that we can take to try to make things better. So now what we're going to do is look at some examples where things have gone wrong and how we can learn from those lessons. So this paper here was from a paleontology journal, and it was actually retracted because they had published the wrong version of the manuscript. So authors had submitted revisions to the manuscript, but they hadn't tracked the changes. The publisher believed nothing had changed and published the previous version. The journal then contacted the authors and said, look, we're going to publish a reference to say, hey, we'll fix it up, but then decided to retract the paper without even consulting the authors. The authors ended up saying in the end they were happy with the outcome. And you can see the link down the bottom. Another one was a Nobel laureate who ended up having to retract a non-reproducible paper in Nature Chemistry. And so when they'd originally published, and then people had started to try and reproduce their paper and were finding errors, the original research group had realized they had misinterpreted the initial data. So it's a pretty big thing to have retracted. Some people do talk about where they've pulled their own papers as well. This was a really interesting blog by a gentleman who was talking about why his lab had moved from other analysis tools to R, which is a programming language. And languages like R and Python make it a lot easier to be more reproducible. So he'd worked out that they'd done a whole heap of analysis. They'd realized that they'd made a mistake when they went to go review it for another paper. And basically a few rows had shifted because there was a full stop that was missing in the data file. So luckily for them, it was a correction and not a retraction, but it was a big moment where they realized that they needed to move to something that was a bit more reproducible for their work. This particular paper is really interesting. So there was two scientific labs, both published around the same time, really contradicting results. And so, they spent a little while yelling at each other, being like, oh, I'm right, you're right. But then they decided to work together to figure out why they actually were really different. And so these two labs spent a year trying to work out what the difference was. They swapped people, they walked through every single step that they did. They even took samples and sent them to the opposite labs to get processed. And in the end, they ended up putting two scientists side by side throughout the entire process of both labs. And what they worked out is at one particular step, when they were mixing a solution together, one sample was stirred at a speed for 8 hours, and the other one was gently rocked from side to side for 12 hours. And that simple change meant that they got vastly different results. And this was really cool, and they got a paper out of it, and it was really fascinating because they made some really cool discoveries. But knowing exactly what steps they took was really, really important, because otherwise they never would have had this happen. So today we're going to look at 9 steps that can safeguard us against any of these situations. We'll go through these individually, step by step, but just to give you a bit of an idea, we're going to look at things like documentation, de-identifying your data, naming conventions and folder structures, automation and version control, working with the cloud, persistent identifiers, and some computer security stuff as well. But what we're actually going to do is look at this in context of some scenarios. So imagine one day, a key person from your lab disappeared one day. It could be the person who is your lab manager or your second, not necessarily the lab head, but the person under that, one of your middle researchers or early career researchers who has had to take off suddenly. Family, personal emergency, they no longer are contactable. Have a think about your lab and your work. And could all the work in your lab continue? Do you guys know where all the data for the lab is stored? And could you effectively keep running for 1 month or 1 year without having the knowledge that that one person had? I really like this comic. Definitely shows you the difference between movies and real life. But mostly, most of the time that information isn't already conveyed. A lot of the times people just assume that, yep, cool, no problems, we'll work this out later, and don't actually think about, cool, like where did you actually store all that information? And we're going to go through this step by step on how to help with that. The very, very first thing I can do is talk about our first tool, looking at documentation. So this is our step 1. One of the things I'm going to recommend as well is throughout this talk, write down on a piece of paper steps 1 through to 9, and write down one change that you're going to make when you step away from this. Throughout this session, one of the things Julie and I are really passionate about is you don't have to go from 1 to 100%. As long as the whole idea of this course is basically to take the next step down the path of reproducibility. You don't have to become an expert. You just need to aim for better than what was yesterday. So the idea of documentation is writing down all the procedures and processes for your research project or lab, so somebody from the outside could come in and understand how everything works. So it can be everything from my files are stored here, my samples are called X, we use SPSS to analyze, everything like that. It could include the copy of where your lab notebook is saved, or having that in a digital format and backed up perhaps somewhere that your supervisor can access it. It's really important to make sure that when you do back things up, that it is accessible either to your supervisor or to your entire team, ensuring that that sharing is done in the proper way. So making sure that people who do need to have access to it do. The best person to start documenting things in your lab is a brand new staff member, because they don't know anything, which is brilliant because they need to go and learn everything. They are the prime candidate. And it also helps them to get familiar with how your team works as well. So getting them to write things down as they learn in a space that is shared is really, really important. Bus factor. So in IT, we have something called the bus factor. And a bus factor or a bus number is, in a project, how many people in that project need to get hit by a bus for that project to fail. I've also had this being called as the lotto factor. So if you have a large chunk of your project that depends on one person, and that one person has knowledge that nobody else does, if they disappear, that project will fall over. So the idea is to encourage information to be shared at least across 2 people throughout an entire project. Documentation also plays a really important part in any audit for your lab. So especially instead of having to frantically trying to pull together information when you know an audit's coming, everything's already prepared and you don't miss any detail either. I saw this once and I thought it was really beautiful. Documentation is a love letter to your future self. So we obviously remember what we did the past day or two. We generally have a pretty good idea of what we did last week, but who remembers step by step what they did 6 months ago? I know for myself, especially if I'm doing anything somewhat tech related, I do not in the slightest remember what I did 6 months ago or why I did it. So writing down notes and making sure I have a good understanding of what process I ran and why I ran it is really, really important and does my future self a really good benefit. So how do we start doing this? And this is the moment you can start writing down your numbers 1 to 9. Firstly, have a read of this Documenting and More document. So it has a whole heap of different things to get you thinking about what you can write down. And you can start saving that literally in just a Word document or a text file. It doesn't have to be any sort of fancy place. Or if you're using, say, eLab notebooks or online documentation portals with your team, definitely the best place to start writing it down. But honestly, a Word document that you share inside your team is perfectly fine. Once you've started writing a few little bits and pieces, the next step is to really start going a lot more into detail about how your workflow goes. And thinking again about the whole idea of reproducibility being able to go from your raw data to your finished product. So this can be everything from downloading your function list from SPSS or a virtual lab to the code you use to create it. You could even do things like screenshot each step that you could do as you go through an analysis tool. And once you've got a really good handle of this and you're starting to work a lot more across your team, start thinking about using things like Git repositories or wikis. So building that knowledge base up, not just for yourself, but across a team. Here's some really good resources. These are all clickable and we'll share them as well. Even though the British Ecology book is focused for ecologists, it's absolutely excellent, has some really good tips in there. And if you are looking to do things like starting to use Git, I highly recommend the Software Carpentry Git workshops, so check them out as well. And I'm going to pass you to Julie for naming conventions.
Hello. So what is a file naming convention? It's basically a framework. or a protocol that enables you to systematically name your files in a way that describes what the files actually contain. And also too, it tells you quite easily how it can relate to the other files that you have. And it's probably a really good idea that you decide upon your file naming convention prior to actually collecting any data. And most importantly too, you agree to it as a team. So what are the benefits of using a name filing convention? Generally, this may differ because of the nature. Projects are different sizes, they're different disciplines, there's different backgrounds. But a file naming your files consistently and logically and in a predictable manner will prevent against any chaos from happening. So hopefully your files will be nicely organized, there's no chance of you losing it, and it's going to prevent delays, of course. And ideally as well, the benefits of the file naming convention is that can be read by both the human and the computer. So that when you look at it straight away, you can identify what you're looking at, what the status of it is, and the version as well. File naming also enables data handling efficiencies. For example, it's much easier to process. So that means your project team members might be sitting there thinking, now, what is it? What am I supposed to use? What word did we agree on? When they've got a file naming convention to check, then they know. So that stops that uncertainty and of course to saves them a bit of time. It's easier to facilitate access to your data as well, the files and the retrieval of it. That's the data efficiency side of it. It's also too easier for you to browse through the files. So you can see straight away, you can look at the file names and know what it is that you're actually seeing and what you're looking for. It's harder to misplace rather, or lose your files. And having that logical and known naming convention can also help with the version control as well, which Amanda's going to speak to shortly. It also too allows you to check for any duplicates of records or anything that's obsolete. And also too, with the file naming convention, you kind of are then making sure that you only use as few words as possible to convey the identity of a file. And you would agree to that in some sort of vocabulary at the beginning of the project. So unorganized data can happen to the best of us, and this is a good example here. So Mark Hanel is the CEO of Figshare, and while he was a PhD at Imperial College in London, he actually created this Figshare, which is a research data infrastructure for institutions and publishers and even some of the funding agencies around the world. But when he was a student, he admits that he was never very good at managing his research data. And to the point where he can't find it quickly, he couldn't find it easily. And then when he told them that they were leaving, the former PI pulled an emergency meeting so that she could discuss the emergency around the lab book and the chaos that had happened. So like I mentioned, it can happen to the best of us. No one's perfect. I've done it myself. So what you need to consider as part of your file naming convention, there's a few things. Where do you start and how do you want to do it? You might want to consider, is it easier for the team to retrieve the files alpha or numerically? Is it best around location? It's something that you can need to have a think about and then discuss and agree on as a team. So the vocab, you would choose that standard vocab for the file names so that everyone uses the same common language throughout. So if you're talking about participants, you would then agree on the word that you would say participant. You wouldn't use their names, for example. That's a very basic sort of example. But also to your punctuation, you would need to use the relevant one agreed upon, and you need to do it, the whole time. So you would use, are you going to use symbols? Are you going to use capitals? Are you going to use hyphens, dashes, or underscores? Because that can help. And also too, you would need to agree on the logical use of dates so that they are displayed chronologically if that's an impact for you in your research project. Example of that is just the year, month, date there. But that doesn't always apply. I had a meeting with a researcher. You don't have to use that example is what I'm trying to say. She was an American researcher and she's obviously spent time in America researching and came out to Australia. And then she has trouble converting it over, and so she's never quite sure. So she ended up having to use the month. So it's 05 JUL for July. So, but it helps her and it helps the project team and everyone stays sane, which is the main thing. Also too, you need to agree on the order. You know, what element of the file names should go first? Is it the years? Is it the location? That sort of thing needs to be decided upon. And you can put all that information into like a dictionary, I suppose, a data dictionary, which is basically your vocab, outlines what you've agreed to. Also too, numbers as well. You specify the digits and how you'll be using them in numbering. So files that are listed numerically, will you decide on 01? Or will it be 002 or whatever it is you want to do, you will decide. And you should also too consider using relevant components in that file name to provide the description, the context. So this is where the data dictionary would help, or the vocab. So you might want to consider, again, the most important component of the research. Is it that location? Is it participant information or the chronological order? So also too, you need to consider versioning as well. And if so, is that part of the file name? Should that be part of the element? Some characters may have special meanings though to some operating systems. So you might want to consider avoiding some of these. And there, I've got them listed below. Also too, for more information, you can have a look at the IBM website. That's a pretty good place to go. Just might save a little bit of heartbreak later on down the track. So this is just a quick example of what a file naming convention might look like. So this project's using sensor equipment and they're doing it at particular locations, and of course they're applying the date. So that's how the structure would be agreed upon. The first red line there, the years, month, date, and then the site and sensor, the file name. And so when you would apply that to your research project, it would look like below. So that's the year in full, the month, and then the date. So that's 21st of June. It was done at Southport and they collected humidity, and it's a CSV file. So also too, you need to agree on a few other things like capitalising the first letter of every new word with no intervening spaces. Is that something that you should consider and agree upon? And keeping file names a reasonable length as well. And make sure that you keep the file name information, the metadata, separate. And you can do that easily by using uppercase. So the example there on the second dot point, image 02 Pacific Ocean, and then the year, and then the file. Also too, that use that logical order for sequential numbering. Instead of 1, 2, 3, try the other options that are available on the screen. For version controls, did the project want to use V1, V2, or will it be multiple, V1, V2, version 2.1. So again, it depends on your project. It depends on what equipment you're using and how important version control will be to your actual project. Also too, there is a document that you should consider adding in here as well, which is a README file text, and you can share that anywhere in your project. It's very useful, and I'll talk about it a little bit further along. It sort of touches on what Amanda shared initially. So how were you doing this? As a beginner, you can just look at some easy file naming conventions. Have a look at the ones on your computer currently. Is this the option? Is that preferable for you? Or do you need to add more information into it? And the other tip here is you might want to try and avoid spaces in your file names as well, because sometimes they don't always play nice with operating systems. The University of Edinburgh, they have a complete and comprehensive list. It's quite good. I'd recommend and suggest that you have a look at that when you can. And then finally, in an advanced sense, you could look around at your project. Does your research team have a project or a policy rather around file naming conventions? And is there somebody in the team responsible for data management? And if not, maybe this is a good way for you to have a chat with the team and get everybody on board to make sure you're doing the same thing. There's some external resources for you to check. And Amanda said they're easily clickable, take you straight to it. So now we are moving on to folder structures. So while computers add basic information and properties to a file, such as the file type and the date, timing creation and modification, it is also for the data handling efficiencies, and it represents essential information in the folder structure. So think carefully about how best to structure folders you want to make easy to locate and organise files and versions. And this is particularly important when you're working in collaboration, not only with researchers in your own institution, but external to you as well. And you need to consider the best hierarchical structure for your folders. So, I have one coming up shortly, but the files can be organised according to your needs around the project. So you might just want to, file it around data, your structures. There's different datas for most projects. There's databases, there's text, images, sound. And then you've got the administrative side of it as well for the research project. You will have copies of interviews and surveys and focus groups, etc. So I suppose having a standard folder structure can keep your files neat and tidy and save you time looking for your data. And it can also help with sharing the colleagues, as what was mentioned earlier as well. So a README text file could document everything that in relation to the project that would be helpful to new project members or your future self. So the structure of the file naming convention and the list of the metadata or file naming information, abbreviations or keywords, that could be included in that README file. You can have anything you like in that README file. It can be bigger than Ben-Hur, or it could be just simple and to the point around folder structuring and naming conventions. And it is considered part of the documentation process that Amanda talked about initially, but we like to remind people that it's not a bad idea to pop a copy of that into your folder structure as well. Now this is an example, and I hope I haven't scared anyone here, but it's just an example of what a project folder structure might look like. So we can see at the top of it, we've got the education project. That's the main yellow folder right at the top. And then underneath that, we've got two blue folders. One's for around data and the other one's called project documentation. So in terms of going back up to the first blue folder, the data, there's different data that's collected throughout the project. So if your project is one that's going to be investing a lot of time and energy around collecting data, you might want to consider doing something like this. So we've got one folder there is going to, the first one underneath the blue, is going to capture the literature review data. So you might have different databases search that you might want to place in each of those folders. Of course, you're likely to have a copy of it in Note, but there might be something that you might want to pop into the folders as well. Notice too, you've got a second folder, major folder for the raw data. So that can include or capture the raw data that you collected around your surveys, using by tools or interviews, or also to any film perhaps. The next one down is the process data. So you can have different subfolders for that. So the survey's been cleaned, processed, so you can pop it into your survey or the interview or the film folder, whatever's relevant, I suppose. And then we've got the aggregated data as well. So data that's all been looked at, you've used and analysed is a completed folder. And then there's a publishing data folder as well. So I've just tried to come up with a general idea of what it may look like. You might just have one blue folder, you might have two blue folders. Again, it depends on the structure of your research. It's kind of like when you start a project, in your concept mapping, you've got your major concepts and you've got your minor concepts. And this is how I pretty much explain folder structure creation to researchers. It sort of helps, and it really does. When you do it that way, you can see exactly what folders you might want to consider. So the second blue folder, that's around project documentation, so your research activities. So any forms that you've used, the consent forms or survey forms, you can have a copy of the ethics application in there, or a copy of the data management plan. So there's also, or even authorship agreements. So this, again, it was just to give you an idea what one might look like. So to develop a logical structure for your team, consider checking to make sure there's no already pre-existing folder structures agreements if you're just new to a project. Name folders appropriately. Don't use your staff name. I've seen that done. And also to consistency, make sure you use the agreed structure hierarchy, because that's really important for making sure everyone's on the same page, everyone knows where data is, and no one's going to be missing any or constantly searching for files. It's in this day and age, a lot of us are either participating or engaged with other external universities or you know, we're online and currently we're at home, so you don't really have the option of putting your head up over the petition and asking your colleague, what do we do with that file, kind of thing. So, and also too, you need to consider the structure hierarchy. So I've already mentioned that. That's kind of the concept mapping, if you like. And also too, it's a good opportunity for you to, when you're doing it, to separate your ongoing and your completed work as well. So that's going to help remove the older documents that you don't really need because, you know, you've moved on to other areas. And of course, backup. You have to make sure that you've backed up your folders and your files. Most institutions will have sound storage solutions like we do here at Griffith. And Amanda's going to speak a little bit more about that, but if your organisation has that, you need to have a chat with them. You can always start with librarians. They're pretty friendly people, and they can put you in the right direction if you're not too sure. And also too, you need to clean up the folders. That's post-project as well. So in terms of a beginner, where do you start? So as Amanda mentioned, you grab your pen, and maybe for this step, you can just have a look to see what it is that your data set might look like and how they could be organised. Maybe use the concept mapping approach first, and that will help you decide upon the particular hierarchy. Okay, and you can also do the next level up, see if you can devise a better naming convention. So maybe note one or two improvements that you can do to the way you capture your files currently. And you could also create a folder template and put it into a downloadable location for the entire project team to access. And then we've got here, the advanced one is, why not come up with a policy for your group, or a process, might be a better word, for folder structure and file naming convention. And if you have several data collections, consider maybe creating separate data folders for each one. External resources available there. There's one where you can download for templates for your folders. And now I'm going to hand you over to Amanda, who's going to be talking about automation.
So let's look at automation. So thinking about what repetitive tasks you do every day or quite commonly, and could you automate it? So tasks that need to be done over and over again by a human give opportunities for human error to sneak in. We're not machines, we're humans, and as much as we try to do something the same over and over again, mistakes do happen. So setting up an automated way of doing these repetitive tasks can eliminate human error, but also can just make your life a lot easier. And we can talk about a whole heap of different ways of doing it. It doesn't have to be anything particularly technical. It could be an Excel formula or a macro, or even just a data science framework can help. So thinking about repetitive tasks that you could automate. Thinking about, like, if you transfer data constantly off USBs, do you rename the files the same way? So perhaps starting to use that file naming convention Julie just talked about, or even just manually copying files across from one computer to the other. Here's a whole heap of different tools you could use to automate. So there's spreadsheet macros and formulas. Mac OSs have a tool called Automator already installed. And so you can actually do some really cool, funky things with that, like automatically rename files and move them to a specific folder as they come into your computer. It can run tasks, say, once a day. So once a day, it might look for emails of a certain name. Windows 10 Task Scheduler is pretty similar as well. If you're using the SharePoint or Google platforms, you actually have a couple of ways being able to automate things in those environments. Microsoft has Microsoft Flow, or Power Automate, I think it's called. And Google has Google Script, so you can actually write code for that. And so you can take emails that you get, you can put them into spreadsheets, you can automatically download files, all that kind of fun stuff. You could actually look into learning Python or R as well. So these are programming languages. R is made for a programming language for people who do heavy stats. Python is a bit more of a generic programming language. Both are really good to learn, especially as in the data science space, but not just for them as well. Everybody can learn how to program. So I highly recommend getting in touch with your local hacky hours or software carpentry people to start getting some lessons there. You can pretty much jump straight from your beginner to your advanced. As you go along, what could you code up so that way everything is completely automated? So, going from beginner, intermediate, advanced could be just building up your automation as you go. And don't forget, this isn't just for human error, but can save you a lot of time, which is really nice. Let's also look at version control. So version control is basically a way of keeping track of changes in your data or your process. So it can be everything from, keeping track of what version of SPSS or R or NVivo you're using, and keeping logs of what steps you took. It's really cool, especially you could do it if you're doing any sort of scripting, but it could even be just a case where you record your screen as you're going through steps in something like SPSS. And so that way you have a copy of every step you've completed that you might want to refer to later or refer to when you're writing your paper up as well. It's also really important to include any extra libraries. So for example, if you've bought a MATLAB toolbox or a particular library that does something very niche, ensuring that you write down not just what library it was, but what version it was as well. Programs change over time, and this can alter your results if somebody goes to replicate your work post-production. So for example, you might find there might be a way of normalizing images that a program can do. And as time goes on and new versions of that program come out, they might get better and better at normalizing images, which means they change the algorithm. But what this also means is if somebody goes and tries to replicate that same function on a newer computer, they might get slightly different results to you. If I can give you one big one to take away from version control, it's never make alterations to your raw data files. Instead, take that raw data file, put it somewhere nice and safe, and then take a copy and work on the copy only. So you've always got that raw data file to go back to at any time. And this means that if you've accidentally overwritten the data that you work on, or you've worked out that you've got an error in your workflow, you can always go back to your original baseline and start back again. Highly recommend writing down versions of analysis software, and this can be not just software but hardware as well. So if you're using an MRI machine, a microscope, any sort of machine, write down both the company, the model number, and any other identifying information on there as well. And you could honestly just put this in your documentation or your lab notebook. It doesn't need to be anything particularly formal. It just needs to be written down somewhere so you can go back later. If you're doing statistics that need a random number generator, write down what your random seed generator number is, because using that seed, people can get to the same random numbers that you're currently using. So for your number 5, if you're a beginner and you've never done this before, please just take a copy of your raw data and put it somewhere safe to keep. So it can be your local institute's cloud solution. As an intermediate, if you're starting to use programs that have a bit of a workflow, so things like Galaxy or KNIME or a virtual lab like EcoCloud or anything like that, copy what workflow you're doing and save it as part of your documentation. Again, this doesn't have to be anything particularly technical. This could be recording screenshots as you go through something like NVivo or writing down exactly what functions you're using. If you're feeling like you want to get really advanced, start looking at things like Python, R, or MATLAB to build onto not just building that automation, being able to use something like Git, which tracks changes in code as time goes on. There is some really good courses around for Git. Highly recommend them if you are doing any sort of coding. And if you're feeling super advanced and you're already doing a fair bit of that coding, I highly recommend checking out systems like Docker or Singularity. So go have a chat to your local hacky hours or e-research team and to find out a bit of information about that. So some internal and external resources. There's the link to the software carpentry and Git lessons here, but there's also links about talking about using things like SPSS for reproducibility as well. So great. Looking at our original scenario where somebody had left our lab, we've improved our processes and now we're covered. This is awesome. So let's have a look at our next scenario. Imagine you're traveling and you lose your laptop bag with your external hard drives in it, or your office has been robbed. Could you continue your work? Is your data backed up? Is it encrypted? So let's look at a few tools we can use to protect our research. We're going to look at backing up to the cloud. We're going to talk about computer security, which is not strictly reproducible research, but I feel is really important in a lot of these scenarios, and de-identifying your data. So, backing up into the cloud. It's really important to keep a copy of your data in the cloud, and this can be a copy of your raw data, your working data, and your completed data. This means that if something happens to your laptop, whether it's that your hard drive has failed, you've left it on an aeroplane, it's gotten lost through a flight, it's been left on a bus, somebody's stolen it, or even if you have an accidental deletion of your data, your research is safe. So if nothing else for this step, a beginner one is making sure that you know where your research storage is at your university or research institute and getting both your raw, working, and final data in there. Once you've got this happening for yourself, looking at building policies for your teams of where things are saved and making sure that there's a copy of that in a cloud backup somewhere, and ensuring that the location is written down in your documentation. Now let's look at computer security. This is really important, even just talking about protection of your data, because ensuring that your computer and network is secure means you're far less chance of having a data breach or a hack. So a couple of really good tips. As you probably hear normally, make sure you have a good strong password and keeping different passwords for different things. And ensuring that your computer's hard drive is encrypted as well. This means if somebody steals your laptop, even if they don't know your password, sometimes they can still get onto it. And by encrypting your computer's hard drive, it stops people from being able to have a look at what files are there. This goes for external hard drives as well. So if you have an external USB and you're keeping any sort of sensitive data on there, making sure that that external hard drive is encrypted as well. Computers that are encrypted work the exact same way. I know both with Windows and Mac, it's literally just something you turn on in your settings. With intermediate, start looking at getting a password manager, and a password manager is a great place to put your encryption code. So when you encrypt your computer, you'll get a code. Best place to store it is in your password manager. And then if you're looking to really make sure you're getting advanced, make sure this isn't just happening in your office or on your computer, but that the whole lab is following these practices. A little bit of information here about encrypting your computer and a few links. And as we mentioned, having a strong password is really important. If you can use multi-factor authentication, it's really good. So that's where quite often you get asked for a PIN through your email or your phone as well as a password. And always avoiding unsecure Wi-Fi if you can. If you can't, try to use a VPN. So most institutes have a VPN that they offer you. And if it's available, always using the EduRoam Wi-Fi as opposed to any sort of free cafe or airport Wi-Fi that's available. Now let's look at de-identifying your data. So let's look at step 8, separating identifying variables from your data. So sensitive data is data that can be used to identify an individual, species, object, or anything that could potentially bring risk if that data is let out in the public. So it could be personal data, but it could also be things like ecological information about where a species that's really rare is, for example. So a little bit of information about the government legislation and talking about personal information and what it's defined as. So looking at basically anything, any sort of information that can become harmful if it's released out into the public that can be used to trace back to a person. De-identifying aims to basically separate any sort of identifiers away from the research data you want to use day to day. It's really, really good to do right back at the beginning. So you keep your copy of your raw data, you separate any sort of identifiers, so names, email addresses, locations, you store that separately, and then work on the de-identified data. So you can also look at replacing any sort of information you've removed with a code or a key. So for example, you could have, John Smith. You could replace John Smith with the number patient 1 and Jane Smith, patient 2. Store this particular corresponding key and name somewhere safe. So make sure it's stored away. Talk to your institute about where the safest place is to store that, and ensure only the people who absolutely have to have that detail have it. And then have your de-identified data available more so for your research team. This means that when you need to start reproducing your data, or for auditing purposes, you can go back and re-identify an individual if you need to. The ARDC has a really good guide for working with identifiable data. We've included the link here as well. And it's intended for researchers who own that data set and want to be able to share safely. So some tips for when you're thinking about de-identifying your data. Do some planning early on. So before you're collecting research, think about what you do and don't need to have. Retain a copy of your original unedited version of your data somewhere that's really safe. And create that de-identification log, so of all replacements or removals that are made. Store that log separately from the de-identified data files as well. So I usually recommend that any sort of identified information is stored somewhere separately where only yourself and your supervisor have access to it. And put all your research data in a separate store somewhere. It's also really good to identify replacements in a meaningful way. So for example, if you're looking at interviews, instead of just taking out the name of a place, replace it with a square bracket and the word place in there. Once you have your identified data stored somewhere, ensure that you have things like passwords connected to it, ensure that that data is encrypted, and make sure it's stored somewhere safe. Definitely just don't put it on a USB key that is unencrypted and floating around in your pocket. And just taking those reasonable actions to prevent that this data doesn't get lost. ANDs, which is a group that then turned into ARDC, have a really good de-identification guide as well. So have a look at that. And they also have a guide on safely sharing your sensitive data. So now we have all these new tricks up our sleeve. And so if our laptop goes missing, we're better prepared. Now let's look at a project after it's finished. So you've published a paper, and then somebody's published contradicting results to yours, and you've been asked to provide data and methods. Could you? So we've already covered some things today that help us to deal with this. So we looked at things like saving our finished data in the cloud, we've looked at documentation, and we've looked at using versions for your software. I'm going to hand back to Julie.
Okay, thanks, Amanda. So this is the last step, guys. We're on home stretch. In terms of making your research reproducible, as a project person, you can share that data safely with others, or you can place it in a repository. And so by making your data available to others, you're effectively data publishing or data curation. And it's a good practice. As in terms of a persistent identifier, this is something that will help you if and when you make your data available. So an identifier is any label that's used to name something unique, and it's also it could be, you know, as simple as a serial number or a personal name. A URL is also another identifier. A persistent identifier, which is also referred to as a PID, is basically, it's your guarantee that anything that links to it will be kept and managed over a period of time. Sometimes it's agreed and sometimes an indefinite, but it's a defined period. Also too, like DOI, which is what you will hear referred to a majority of the time, which I'm going to speak to foremost, is basically a persistent identifier, and it's a unique combination of alphanumeric strings. So a digital object, a DOI, is, like I mentioned, alphanumeric, and it actually links in a persistent manner to any of the content that you have located on the internet. And so what does a DOI look like? There's a couple examples there. If you click on those DOIs, it will take you to relevant records. And that second click, link rather, or DOI I should say, it actually goes to a record in our Griffith Research repository. And it's when you click on it, you will see the DOI is represented about halfway down on that record. So you can have a look at that to see what that looks like. So effectively, you are making your data reproducible by making it available through that DOI. So who assigns DOI? They're generally done by publishers and also to organisations such as ours. So, for example, at Griffith, the library, they mint the DOIs. In other areas, it could be the e-research or ITC areas. So universities do it, research institutes, and agencies as well. So the DOI also too, it's linking to your unique data. This is post-project. So it also too supports citation and citation metrics, which I think as a researcher is important. Most people know that when they read your article, or most researchers feel that when people cite you, it's because they typically agreed with what it is that you have come up with, or your outcome. So, and the same thing too, so they will cite your article when they use it in their research outcomes or publication. And the same is happening now for research data sets. So yes, they can attract citations, and also to other metrics as well, which is referred to as alt metrics. Thank you. Okay, so DOIs are persistent identifiers, and as such, they carry the expectations of a curation, which means it'll be permanent access, and it's going to have rich metadata, and that means it's going to be well documented, so that people will be able to find it easily, and therefore, in theory, replicate or reproduce rather your research. And DOIs can be created for data sets and other associated outputs. Excuse me, I'm losing my voice. DOIs for data are equivalent to DOI for, like I mentioned previously, your research article. And they're also too now delivered around or presented to people who have used grey literature or developed a grey literature, and any workflows or algorithms, and even software as well. So a DOI is basically it enables accurate data citation and the bibliometrics that I mentioned, and also it helps it to make sure that it's resolvable, which means it's going to work when somebody clicks on it, it's going to go through to the record, and which is going to help in terms of discovery, in terms of people accessing it, for them to reproduce, and if they want to attribute to you, cite you, and also to reuse. So having a DOI will ensure data is available in future for future reproducible research processes. So this slide here that we're talking about, it's pretty much the reason why we do science, isn't it? Science is actually building upon the research or science of others. So open research is one of the key areas, and it's expanded in the open scholarship movement. So scholarly journals and publishers are at the heart of this shift. And with recent years, we've seen an increase in number of scholarly journals with data sharing policies, in that they're aiming to increase transparency and reproducibility of research. So Springer Nature is a good example, and so is Taylor and Francis. So they're two leading publishers who are rolling out on the research data sharing policies. So, and this example here, in quotes, it's an inherent principle of publication that others should be able to replicate and build upon the author's published claims. So therefore, the authors are required to make materials, data and associated protocols promptly available to readers without any undue qualifications. So by you administering or requesting that DOI for your data set and other associated material possibly, you are actually going to meet the needs of these journals and publishers, I should say. There is also too some requirement from some funding agencies that you have to make your publication from your research project made available to the greater community 12 months post-project. So that's generally in an open access or a repository, if you like. So we've got quite a few different repositories. Most institutions have their own. Then we also too have discipline-specific repositories. So if you wanted to have a look at that, you're welcome to do a search and see what you come up with. Also too importantly, and which runs parallel to the reproducible efforts, is in open research. By making your data available through DOI, it's going to contribute to the FAIR principles. So FAIR you've likely heard of to some extent. FAIR means findable, that's the F. A is accessible, I is interoperable, and R is for reuse. So I just wanted to highlight the fact that by making or giving your data set a DOI, yes, you are contributing to the FAIR process and the open research agenda, which is very important and very good, but it doesn't necessarily mean that the data that you have is going to be the A in FAIR, which is accessible. So, and how we get around that is that a DOI which links to a record and a repository, for example, would have a comment there, and it says to request access to this data, you are required to complete this form, which you will complete, and it's then submitted to the owners of the data set. And then you can start that conversation with them in terms of your reproducible research efforts, or perhaps you're a new collaborator seeking to develop some sort of partnership with him or with them, sorry. So that's one of the key messages. So PLOS is another journal that also requires that data that is underlined in any outcomes are fully available. And as I mentioned, DOIs not only uniquely identify the research collection, it also supports those citation efforts. So in terms of the beginner and around what you might want to do for DOIs, you can learn more about your DOIs and just simply watching this video here. It's not a very long one. And you can also too increase your knowledge around the DOIs and the citation rate aspect of it, and the ANS guide that we've got links to as well. So as an intermediate, you could possibly ensure that the data that your last publication, you can make that data possibly discoverable, or give it a DOI, I should say. And so you might want to talk to your librarian or research support librarian and to see where what that process might look like. Pardon me. And also too, by making, as I mentioned, your data discoverable, you're supporting reproducible research and open research efforts. And the advanced is that you can ensure that all of the data for all of your publications have been assigned a DOI. That might take a bit of work, but I think it'll be well worth the effort in the end. So for further resources, we have really good guides from ANS, the citation and identifiers, the DOI system for research data. Have a look at that and learn more about the PIDs and DOIs, again, at that ARDC guide.
Awesome. So that's 9 reproducible research things. So now we're covered for that scenario. What if we looked at another scenario? If a research partner organization has been concerned that your sensitive data has been made available to others, could you show that steps were taken to avoid this? Turns out we can. So we look at things like using own cloud or different tools, cloud tools, and showing who you've shared the file with. We've talked about computer encryption, so making sure that people can't access your computer. We've talked about things like just good general computer safety. And we've talked about separating identified variables, so making sure most people don't have access to any sort of identifiers. So this is excellent. We have so many new skills. So you've got your 9 things written down in your piece of paper. Have a think about what changes are you going to make. Thank you very much for listening to our presentation today, both for myself and for Julie, and feel free to get in touch with us. Thank you.
And also, too, a quick thank you to Martin as well for inviting us to come along and speak to the LADAL Opening Series. Thank you, everyone.
Thanks.